All right, welcome again. For those of you that were on previously, we'll just go through a few housekeeping directions before we get into the content of the seminar here. So this is just a screenshot showing the control panel that you should be seeing on the right side of your screen. We will be accepting questions. They can be submitted throughout the webinar in the questions box. You may need to click on it to open up that field to enter questions. Questions will not be addressed until the end. So if you ask a question earlier, you're going to have to wait a while to hear the answer. So at this point, we'll proceed with the webinar content itself. How do I scroll down here? Just click. I'm John Bratton with LimnoTech in Ann Arbor, Michigan. Our speakers today will be in the order listed. The first will be Brenda Schneider from the University of Toledo, second Ed Verhamme from LimnoTech, and finally Paul Nieberding from Fondriest Environmental down near Dayton, Ohio. So the topic today is real-time harmful algal bloom sensors for drinking water treatment. Anybody that's on the call today probably has an interest, either scientific, regulatory, or actual hands-on utility management backgrounds. You're all familiar with the particular algal blooms in your region. We will be focusing primarily on algal blooms in Lake Erie today, and I've included a map of North America because we do have some participants from abroad who may not be familiar with where Lake Erie is. We're expecting over 300 participants today from 37 states and 6 countries at last count, including many particularly large group from US EPA, both at headquarters and out in the regions. So thank you for registering. So many of you are familiar with Lake Erie, but I'll give a very quick background. This is a MODIS image, satellite image from 2015, this fall in September, showing the maximum extent of the bloom from both the western basin and then continuing out into the central basin, 2 different types of cyanobacteria here. So a quick introduction. Harmful algal blooms are harmful for many reasons, but particularly because of toxins, especially neurotoxins and liver toxins. They are generally agreed to be caused by excess nutrients of various types in particular water bodies, especially common in warmer waters during the summer and early fall in areas that are strongly seasonal. The horizontal and vertical movement of both organisms and currents and wind mean that it's hard to predict where they might happen to be at any given time. That will become important in some of the later presentations. And also toxicity and the properties change over the course of a day, a week, or a season. We're going to focus on water treatment plant operations today for several reasons. Cyanotoxins are unusually potent toxins. Vulnerable populations are particularly at risk. The young, the elderly, people with compromised immune systems or other illnesses. Treatment approaches may need adjustment to remove the toxins. The guidelines for toxin levels that are considered safe for various populations are very limited at this point. Testing methodology is still being developed for many. And traditional public advisories may not be appropriate, such as boil water orders. Focusing on Lake Erie, there are information gaps for water treatment plant operators, including bloom locations between notices that are put out based on satellite information. Also, the vertical distribution cannot be detected from satellites, but is important for the depths of intakes. Toxicity can't be remotely detected, and there's usually some delay between a collection and analysis of a sample. The likely movement is not always clear, especially if there's cloud cover for satellites or other sorts of interferences. And other water quality parameters in the lake are also important in the process of treating because they affect the effectiveness of treatment. Another question people have during blooms is what's happening elsewhere, what's happening with other operators up and down the lake shore in this case, upstream on a river, or in a system with multiple reservoirs. So our speakers today will be first Brenda Schneider, who's a senior research associate at the University of Toledo, formerly worked for the city of Toledo for many years, and she'll give a little bit more of her background. Also has held positions with Ohio AWWA sections for research and technology. And she's also a licensed Class 3 water supply operator. Ed Verhamme with LimnoTech here in Michigan is environmental engineer. LimnoTech's an environmental consulting company based here with also East and West Coast offices, specializing in water science and engineering, including modeling, monitoring, permitting, and research. And then finally, Paul Nieberding is general manager at Fondriest Environmental in Ohio. They're a full-service environmental monitoring company providing design, installation, sales, rental, and repairs for monitoring instruments. So the topics that each will focus on today, Brenda will talk about the value of real-time HABs sensing from a real hands-on water treatment plant operator's perspective, and she also has a chemistry background. Ed will talk about the value of having a network of sensors, and then Paul will give some practical description of sensor details. So at this point, we will switch over to Brenda.
Good morning, everybody. As John said, my name is Brenda Schneider. I'm now at the University of Toledo and formerly at the City of Toledo. During the crisis that happened in August of 2014, I was the chief chemist. A little bit of my background here. I have degrees in both chemistry and biology. I was with the city for 15 total years, 6 of them as chief chemist. As John said, I have a Class 3 water operator's license in the state of Ohio. And I have been active in OAWWA, and I'm on the University of Toledo Water Task Force. My task this morning is to hopefully help those of you who are either not familiar with SONs or know about SONs, but not how you would necessarily use them, dealing with blue-green blooms, to have an idea of how they can help you. In the pre-SOND era, before the City of Toledo had a SOND, and they now have 3, but before they had 1 out in the lake, you basically had to rely on your daily plant data. We have an operator that works out at our low-service lift station, pump station, and they also do some readings for us, and there's some automated online equipment. But you were relying on things as they were coming into the plant for the most part. We also had, as has already been mentioned, the NOAA HAB bulletins that came out about once a week during bloom season, and if you got on and accessed the satellite images, you could bring down MODIS images of the western basin of Lake Erie or the other Great Lakes. Oftentimes, those 2 items had limitations. It's because they come out weekly. And what's going to come up here on your screen is a series of these bulletins from July, the end of July to mid-August of 2014. And you can see in the second slide that's there, the second bulletin, that's from August 1st, the day that we got the high reading on the microcystin and had to issue a do not drink order at 2 o'clock in the morning. And as you can see by looking at that HAB bulletin, there's not a lot there. There's some, but not a lot. So the limitation of the bulletin is that it was once a week. This past summer they were trying to do the bulletins twice a week, and after the do not drink order, NOAA geared up and they were putting the bulletins out twice a week, which was beneficial. But you still only are getting them infrequently, and the data is old once you get it because they have to process it. The data that you're seeing is usually a day or 2 old. MODIS imagery, which is wonderful when the sky's clear, but oftentimes in northwest Ohio, it's not. These images start with July 25th, run across and then down and across up through August 4th. And you can see that it was August 4th before we had a nice clear image. when you look at this image here, you actually, I mean, you can see there that there's a bloom in the lake, and it's visible on the satellite. When you look here, which was July 31st, the day before we had the high reading, it's very hard to tell that there's anything going on near our intake, which is about right there. So again, very good tool when Mother Nature cooperates. Unfortunately, Mother Nature does not often cooperate in this part of the country, and the same thing happens other places too. So before the 2014 incident, the City of Toledo basically relied on the satellite pictures, the HAB bulletins, and monitoring pH, because as a bloom grows, the pH of the lake water increases as CO2 is removed by the algae. And I've got a slide a little bit later on that will show you that over a period from spring to fall. After the 2014 incident, when we got the probe in the water, and our first probe on the buoy about 1,000 feet from the intake crib went in the water late in the day on August 7th. So 6 days after we had the high reading, we had a probe. And after that, with the probe in the water, the sonde, with a phycocyanin probe and a chlorophyll A probe, we had readings on how much, giving you an idea of how much algae was out there and how much of it was blue-green. We still had the satellite pictures, we still had the HAB bulletins, and we still had the pH monitoring at the pump station. We get into the sonde area that gives us the ability to have continuous sonde data, continuous monitoring of pH, temperature, conductivity, turbidity, chlorophyll A, blue-green or phycocyanin. Still have the satellite images from NOAA, the HAB bulletins. One of the nice things about the sonde, as I'll show you here in a few minutes, is you can look at your data. You can go into the websites that the sondes report to, and you can look at your data over a period of time. You can download it, you can archive it, you can take a screenshot of the computer if you want to, you can make graphs. It makes things, gives you a lot of information. So first slide here gives you just a shot of the web page that if you go to the City of Toledo's Lake Buoy sonde, this is what comes up, and you can see that there are a number of parameters that are monitored. This buoy has a weather station on it, so it monitors wind direction, wind speed, wave action, air temperature, water temperature, in addition to chlorophyll, phycocyanin, pH, turbidity, etc. And you can see a nice picture of the Toledo intake crib, and the bottom picture is a picture that was taken just this past summer. I believe August 10th is when that picture was taken in 2015. Didn't hear a lot of things about a lot of toxin in the water, but there was a lot of algae in the water. Going to switch over here to the web to show you. So this is the low service pump station sonde at the City of Toledo. And the reason I'm using that is because the two sondes that are out in the lake, the one that's on the buoy and the one that's at the intake crib, have been removed for the winter because of ice and the fact that they could be damaged. But you can see on this site that you can bring up, this is today's data that's coming up here on the screen, December 16th, right? And I'm going to use pH because at this time of year other things aren't changing very rapidly, but pH still does show some changes. And we did a calibration of 24 sondes this past Monday, and you can see where the sonde at low service was removed for that calibration and things dropped down and then placed back in the water. One of the nice things that you can do with this tool is you can change your dates. and look at things over time. And try to quickly here, because the computer reset on us. This should only take a second. So this, you're looking at pH from May 15th to October 15th of this past year. And one of the things I said, when you're monitoring and looking at these blooms in your source water, blue-greens and normal algae, green algae, uses CO2 in the photosynthesis process. You can see in this slide where during spring runoff, pH has dropped down and at one point reaches about just below 7.6. To coming into summer and coming into the height of the bloom, you have a pH, this is in the raw lake water, coming into low service of 9.4. That's a significant pH swing between spring and summer, and then back into fall, where it drops back down. So you can set any dates for that you want to look at graph data. So one of the other things that I wanted to show you is down at the bottom of the screen, the original screen that you come up to when you come in on the web, there's a chart that shows you the last couple of hours of observations, which you can just look at or you can download. And you can download this data so that you can use it in an Excel spreadsheet, save it to your computer. You just click on the download data, input the dates that you want, click Get Data, and it will download it as a comma delimited or tab delimited file into an Excel if you have Excel on your computer. It's quite a nice feature to have. Also included here is a list of descriptions of what all of the different abbreviations that pop up when you download the data or look at it in that screen shows you. Because not everybody knows what YSI term NTU means, right? But it's, you know, turbidity and NTU, it's just an abbreviation. Some of them, this one is fairly straightforward because it's got conductivity, total dissolved solids, oxidation reduction potential, things that we commonly know. The fun one to look at is the one from the crib, from the buoy, that has all the weather data on it. That can get really interesting to try and figure out what all that stuff is. These sites that I've been showing you are the direct link to the SONs through finding it easier to go back through the Great Lakes Buoy site. When you bring that site up initially, you see a nice map of all the buoys that are on the network. Most of them are not in Lake Erie, although Lake Erie now has its fair share. And below that is a table of all the different buoys, and you can choose any of them. So one of the really nice things about having the buoys in the lake and in the water plants at their low service lift station or at their crib is that you can see data from other places. So Toledo and Oregon tend to be fairly close together, and I know we've got Cleveland and Cleveland. This is Toledo's crib, this is Toledo's low service pump station, and this is the buoy link. So you can go in and see all of those. There is also a HABs data portal that's been set up by the Great Lakes Observing System, where this you can use pretty much the same way. It comes up with whichever station. I've already clicked on the Toledo low service pump station here. But when NOAA Glural has their buoys out, you can look at their data. The Oregon pump station, Ottawa County, Avon Lake. Little Cedar Point is the University of Toledo's buoy when it's in the water. Most of these have been taken out for the season. Some are still in. But you have the ability here also to bring up a piece of data. So if I want to bring up pH here and use those same dates that I used before, and I click refresh the plot. Now you see a similar plot to the pH where you've got a low and a high at about over 9. You can download data using this tool. So these are two of the links. The top one is the one to the last slide I showed you, the last website, and the second one is the one I was using the most, the GreatLakesBuoys.org. These are two of the graphs that we had. We stuck them in here just in case the live did not work, so you've already seen those. You know, when you're watching, looking at this data going in daily, you're watching for the blue-green algae and to make changes to your treatment. The earlier you know you have something going on, the more rapidly you can make changes to your treatment to prevent having a problem in the water. Hopefully also, by watching these graphs, you can adjust your treatment accordingly, not just up, but also down. So you can see as the level of, this is a blue-green algae graph here, as the level of the blue-green algae drops off, you could cut, for instance, your carbon treatment, or you might be able to cut the alum addition because you're not getting as many salts into the plant. For those who don't know, this is from the Ohio EPA website. I downloaded this last night. It shows the harmful algal blooms at water treatment plant intakes this past year. This is blooms, not saying that there's toxin there or not saying that there's any kind of problem with the water. This was just where they had blooms at intakes that could potentially create toxins. The advantages for a treatment plant, I think I've already outlined these, but to go over them again, your early warning system, your sondes, you check your sondes around your water intake at your low service, wherever you have them. You can use them if you have a weather station on them to look at drift based on wind and weather, depending on the depth. So like Toledo, the buoy sonde is in about 2 feet of water, the crib sonde is in about 10 feet of water. It gives you a very different look at what's going on out in the lake, even though they're only 1,000 feet apart. You can watch your incoming raw water more closely, and you can adjust as values change. The other thing that you can do, as I said before, is you can download things and maintain them for records.
Do you have anything else, Brenda?
Just the last slide, just having these tools allows chemists and operators to be proactive and anticipate what's happening with the water and make treatment changes that hopefully will keep any problems from happening so that the citizens and industry doesn't have to worry.
All right, thanks Brenda. With that, I'm going to move into my presentation. This is Ed Verhamme from LimnoTech. And I'm going to be talking, just kind of building off a little bit of what Brenda said. You know, I started working with Brenda immediately after the Toledo water crisis. We got very familiar working for her, and it was really trying to help them understand what was happening with their source water, as Brenda was discussing, and you know, providing these online tools. And it, you know, there was other water utilities within the region that were impacted by this HAB, and they also became interested in some of the same technology that Toledo was using, and so we've tried to work with other utilities on Lake Erie And so the title of my talk here is From Toledo to Ashtabula, Why Online Monitoring Pays Off. And I think, so we just installed a sensor in Ashtabula, Ohio, which is kind of on the far east side of Ohio. And just a quick overview, I just want to briefly some HABs resources and management strategy, and then also talk about when and why to share this data. I think Brenda covered some of the basics on why operators want the data for their facility, but I also want to discuss why other people might be interested in that observation as well, and talk a little bit about how to share the data. And then Paul's going to follow up with some of the logistics of the sensor that we're using and the costs. I just wanted to just put up some of these HABs resources for utilities. These are very recent documents that have come out from the US EPA and AWWA, and they're really, as of just last month. So the US EPA has a algal toxin risk assessment and management strategic plan for drinking water. That's kind of their working document. They also have information on the health advisories that are listed for cyanotoxins, and they also have recommendations on how individual water treatment plants can manage cyanotoxins. And so I'm just going to walk through just a few basics of those plans and how I think SONS can help. One thing is, if you read those documents, some of them are more planning based. They're steps, but they're not very detailed. And there's very little information of online sensors and how you could potentially use those in your operation to save money and also increase your confidence in what's happening with the source water. So if we look briefly at the US EPA's HABs management strategy, I just pulled this from their document. They have 5 steps here. The last step I didn't show, step number 5, but the first step is a source water evaluation. Is your source water even vulnerable to a HAB? If it's not vulnerable, then this technology or this isn't for you. You're not at risk. If your source water is vulnerable, you get warm temperatures. People who have seen HABs before, you might start looking. Go to step 2, prepare and observe. So now you're looking for the presence of a HAB, and this is where SONS can start to help. They can tell you if a bloom is potentially present. It could help you to launch additional field crews to go take pictures, take samples, and then if you verify that a HAB is present, you can use the SON to help track changes in the abundance of cyanobacteria during a bloom. And it can also help you optimize your treatment. So it's more than just a presence absence. It can tell an increasing or a decreasing trend in the bloom. And once you're actually detecting detecting toxins in your water and in your finished water, then you're kind of in crisis mode, and you're really using that SON data to see is stuff going up or down between these toxin measurements that take time to process and figure out what's happening. So just walking through those steps: vulnerable, HAB present, monitor, treat, and continue to monitor. This strategy is repeated in the Ohio EPA's HABs response strategy. This just shows, I just highlighted the spots where they want utilities to monitor their water. So they're observing. You're taking either weekly samples or samples 3 times a week once you start detecting cyanotoxins. So again, between those measurements, what's happening with the source water? People are continuously drinking the water. The plant is continuously running. And so how do we operate and sort of manage risk in between these sampling events? When we think about the plants and this online data, we have the question, when should we share data with others? So all the Lake Erie SONs that Brenda mentioned and that I mentioned are affected by HABs. There's more than one water utility on this source water. So I think if you have multiple utilities on the same source water, then it's kind of a no-brainer that other people are going to want to know what's happening at your
intake. And so it becomes very advantageous for others to see what's happening. But the biggest thing is you as an operator want to know what's happening at those other facilities. So it's kind of a mutual sharing, where if you share yours, they'll share theirs, and you can all see what's happening. You know, it's not just for the water utilities to see what's happening in other people's source water that could be upstream of them. If the water is used as a public beach or for parks, there might be other agencies that would like to use that continuous raw water data to see what's just happening in the source water, and that might help them coordinate sampling for their park. It might help them, again, track changes that's very expensive for them to independently put out, or if they have a station, it's another point in their monitoring network. And also scientific research. I think as we've seen from the date of some of these guidance documents, that the scientific research is very active, very ongoing. And for your source water, it might make sense for you to help other researchers with studying the water body. And so having a continuous record of turbidity, conductivity, pH, chlorophyll, and cyanobacteria is very valuable to a researcher. And it's something that can be difficult for them to install and maintain themselves. So consider sharing that data just for the pure fact that it's going to help you out in the long run, because the scientists will be better informed of what's happening. They can arrange their monitoring to track trends as well. So again, know your source water. This is just a map of the showing the bathymetry. So we can see Lake Erie is by far the shallowest of the Great Lakes. And if you look at where Toledo sits, it's right at the mouth of the Maumee River, which is draining a 5,000 square mile area. That's a very high percentage agriculture, in the 70–80% agriculture. So source water changes are very important to these water treatment plants. This is a map showing all of the public water systems that would draw surface water between Toledo and to the Ohio border near Ashtabula. And I just wanted to overlay from September of this year what the NOAA HABs bulletin looked like of where the harmful algal bloom was. So you can see it's very advantageous for these plants to share data amongst themselves. Again, it'll depend on your water body if it makes sense to share data, but that's kind of how this network was built, of that need to share data. So we worked with GLOS, as Brenda said, to get these sensors all online in a common database system. And it's not just the water treatment plants that we worked with. We also partnered with the researchers at the University of Toledo, at Ohio State University, and Bowling Green that maintain buoys in the source water. So we're able to also put buoy data from researchers in the same system that the water treatment plants are, so the operators can see what buoys are measuring further upstream or further away from them. So again, it's kind of this early warning system. So it's, you know, it's not just for water treatment plant data, it's for researchers as well. And just some of the basics of how to share data. I think some plants say, yes, I want to share data, but what are some of the steps? One thing that we did with Toledo is we just installed a separate data connection, a cellular modem that's dedicated to sharing data. And so for a plant that their primary goal is to get it into their SCADA system, and then a secondary goal might be sharing the data. And sharing data through a SCADA is very difficult, if not totally impossible, given the security requirements. So we've just installed a cell modem right to the data logger that the son's connected to, and the data logger acts as the gateway between the SCADA and a gateway to share data over the internet to, in this case, the Great Lakes Observing System. And then your second step is you need someone to receive that data on the other end. So you need a data management partner. In Lake Erie, this was the Great Lakes Observing System. For other places around the country, you might have an IUCE or NOAA-related organization that could help with this. There's other groups potentially in your area that might help, including the USGS, watershed groups. Again, it's just connecting with some of the people that are working on your particular water body. You can also go with a hosted solution. A lot of companies that sell data loggers might have their own hosted solution to get that data online. We partnered with Fondriest Environmental, and they have an example of their hosted website here. So, and then kind of the second step is, so the data is, quote, online, but what's the best way for people to view that data? Brenda walked through some of the different graphs that we've set up for this Lake Erie case study of showing time trends, being able to download data, what are the most recent observations, and that tool that Brenda walked through from Gloss allows us to show multiple stations on one plot. And again, here's just a snapshot again of that data viewer. It allows you to view data from multiple stations, buoys from researchers, sondes from water treatment plants, all in one site. And this is just a snapshot of the Fondriest's hosted data solution, WQ Data Live. One note I also wanted to mention is there's more than just the sonde data that's happening. Brenda mentioned the other sources of information that might be used by operators, whether it be a NOAA-issued HAB bulletin, MODIS satellite images, data from other researchers. And so one thing we worked to set up this year was sort of an all-in-one website, and it's just more of a tabbed website that links directly to other agencies' data sites. So we can share with this one link the NOAA HAB bulletin, our sonde monitoring data, the MODIS images. And so just trying to really simplify the experience for a chemist or an operator of trying to assess what's happening right now. I think larger cities are a little fortunate to have a position as a head chemist. A lot of smaller plants, it's kind of done by operators, and in between shifts, and it might be that the first 5 minutes of their shift they have to assess what's my bloom potential today. So very limited time frames to think about what's happening with my source water, amongst all the other job responsibilities that are full. So, in some ways it's turning water treatment plants into a little bit of a scientist, and that they have to look at what's happening with the water body and how it's changing. And again, trying to make tools that make that easy to try and show bloom present, bloom not there, and those online sensors, even allow them to track that data even when they're at home. If they want to see the trend, if they're coming into a shift, you can just check on the website and see what's happening. For the superintendent, that's not going to be there all the time. He can check in and call in and see that raw water data as well. So again, for source water that is changing hourly, daily, it's very valuable to help track those changes wherever you're at. And again, just kind of reiterating what Brenda said is showing how these sondes can show the presence and absence of a bloom. This is the Toledo pump station data from 2015, just showing and this is daily average as opposed to some of the raw values Brenda was showing. So we can see that the bloom started about early August. The sonde jumped up. The sonde stayed up for many weeks, and then it started to decline as the water temperatures cooled off. So we can really, and then here I wanted to overlay the microcystin data on top of the sonde data. That's the phycocyanin parameter. So we can kind of see that the sonde is tracking the toxin concentration in the raw water very well. Toledo monitors every day, so we get a really good relationship or a really good data set to show how the sonde data compares. We can see pre-bloom, low toxin, during the bloom, higher toxin. At the die-off of the bloom, we can see the sonde and the toxin are tracking down. I also wanted to show the standard deviation on those daily values. So you can see the sondes, even early in the season, the sonde was indicating something was happening around late July, and it spiked up, and again, the daily average was low, but those 10-minute values, several of those were very high, and so the bloom was starting to develop here. And for this case here, roughly 10 RFU was 1 microgram per liter. And the sonde is a toxin measurement. It's not measuring toxin, it's measuring, it's a blinky LED that correlates to the phycocyan concentration, where it correlates to to cyanobacteria biomass, and Lake Erie cyanobacteria biomass correlates all to microcystin. So if we can start to empower operators to see how toxin concentrations might be changing, that could help them to optimize carbon rate additions. It would help them to potentially collect additional samples if they would like to see where toxin is trending. If I look at 2014, this is the daily average 2014 data. The sonde again is the red, and the toxin is the blue circles. The Toledo water crisis, we don't have data from the sonde during that period. We have it after the crisis. So you can see several days or after the crisis, the bloom was back. Toxin levels were back up again in the raw water, and we can see the die-off into the fall. And one thing to note here is in 2014, about 1 RFU was 1 microgram per liter of toxin. So, it's an order of magnitude difference in the RFU to microgram per liter relationship. So, I'm saying that the sondes even can tell you, that you can use that relationship from year to year. You have to collect the toxin data, but the sonde will correlate an increase or a decrease once you start developing the start of that relationship. And there's that happens. You can see the sonde dipped here, but the toxin stayed up. Lake Erie is very dynamic. Wind is changing. The bloom is being pushed around. We're having mixing happening. So there's, if I were to show the chlorophyll this period, the chlorophyll did stay elevated, but the phycocyan dropped. So it's not a perfect solution for one jump this way, one jump that way. But again, it's another tool and it's continuous. I just want to show the city of Oregon's data here real quick. So Oregon's intake is within less than a mile of the city of Toledo's water intake, so very close together. But they only collect weekly samples for toxin. So you can see that with the green triangles here, this is toxin measurements, and the black line is the kind of daily running average sonde measurement. So we can see a better relationship. We can see how an operator, if they didn't have the sonde, would be surprised that all of a sudden we go from toxins in the 1 to 6, but the sonde would clearly indicate that cyanobacteria was rising. And so, again, the sonde is just a tool. There's other parameters the sonde is measuring. Brenda mentioned those as well. And then, oops, sorry here. And with that, I want to make sure I had enough time for Paul here to describe the system. So I talked about some of the parameters, and then I'm going to turn it over to Paul to talk about the system as fast as I can. Thanks, Paul.
Thanks, Ed. Good morning, everyone. So what I want to get into is a bit more about the instruments being used in the Lake Erie network specifically and throughout Ohio. You can see an overview of what I'll be talking about here this morning. Talk briefly about the company, get into the YSI XO2 sondes that are being used, basics of configuring, and get into some of the pricing as well. So just a little bit about our company, Fondriest Environmental. We're located near Dayton, Ohio. We are a nationwide distributor for a variety of product lines focused on natural resource monitoring, but we're also the exclusive rep for YSI XO and 6 series sondes in the Great Lakes. We have a sister company called NextSense Technology that manufactures data buoys, data loggers, and we've partnered with LimnoTech, Ohio State, NOAA, and other organizations on providing these integrated data buoy systems. So just an overview on the YSI XO2 sonde itself. The word sonde is a French term for probe, so that's where that comes from. But it's basically a platform for installing multiple sensors and outputting data. Some of the features of the sonde, it's titanium bulkhead with weightable connectors, which makes it very nice when installing and removing connectors. You don't have to worry about moisture. It has Smart QC to check for any faults or errors with the sensors themselves. There's an assisted calibration that helps walk you through the calibration process. And all the sensors are smart, meaning that the calibration data is stored on the sensor rather than the sonde, making it easy to swap sensors in the field. Getting into the temperature, that's kind of the base sensor that's required. You can get it in a wiped configuration to keep the sensor clean, and it will also calculate and output the salinity, specific conductance, and total dissolved solids. pH is another available sensor with optional oxidation reduction potential. Dissolved oxygen is available as an optical sensor. Turbidity, that also will calculate and output the total suspended solids. And then you have the total algae sensor, which Ed and Brenda were referring to in their presentations. That's a dual channel sensor, so it will distinguish between chlorophyll and phycocyanin. There's also a saltwater version available that's dual for chlorophyll and phycourethrin. Finally, there's a dissolved organic matter sensor available. The F in FDOM stands for fluorescent dissolved organic matter, and depth or level option. Specifically on the total algae sensor, you can see kind of a rendering of what that looks like on the left. As I mentioned, it's a dual channel sensor, and it will output data in raw fluorescence units, which is just an uncalibrated value, or you can also calibrate to micrograms per liter. That's with the blue-green algae and the chlorophyll. So a few reasons why the XO2 was chosen for this network. It has the dual channel total algae sensor, as I mentioned. There's also room for 5 additional sensors, which basically allows you to measure many other variables besides algae. There's an active wiping sensor mechanism in the center there that will clean all the optical sensors and all the sensors, including pH and conductivity. You can see the picture there. The sonde itself is quite dirty, but the important optical faces are kept clean. It's also an expandable platform for additional sensors as they become available. There's an auxiliary port on the back end of the sonde for sensors that might not fit into the bulkhead there as well. So just the basics of building an instrument. You have the sonde with integrated depth or level, if that's of interest. There's a USB adapter that's used for calibrating the sensor, configuring the deployment, and also data upload if you're using the internal data logger. That's a picture of the central wiper there. That's pretty important on any in situ deployment. And then the available sensors, you can see the total algae sensor there, conductivity and temperature, turbidity, pH, ORP. You'll see that black plastic portion. That's a consumable module that needs to be replaced every 18 to 24 months. There's the optical dissolved oxygen sensor listed there, and finally the dissolved organic matter sensor. So in this network, the system components, you have the XO2 sonde that can be on a mooring frame, deployed inside a deployment pipe, or attached to a data buoy. Next, you have the data logger with some sort of telemetry. That can be radio, that can be cellular, it can be satellites. You could also do a cabled connection to a PLC if you're working in a water plant. And then finally, the real-time access to the data, that can be through a software program, through a web data center, or through a SCADA system if you're just looking at the data internal to the plant. I wanted to show a couple of photos of typical deployments. This is a wet well deployment here. Generally, the sonde would be deployed in the wet well right before the traveling screen. Cabled connection up to a box there, and hardwired connection to the data logger. And inside that data logger, you have the wireless module to transmit that data back. This here is a photo of the buoy deployment at the City of Toledo's intake. One advantage of having a buoy deployment is it can support multiple additional sensors, weather station, current meter, webcam, wave sensor, thermistor string to get a full temperature profile, and any other sensor that would be compatible. As Brenda mentioned, this buoy was delivered within, I think, 6 days. We worked with them. We worked with LimnoTech to supply that buoy, get all the equipment integrated, and then LimnoTech was able to deploy that in very short order. Finally, just want to talk about comparing data. One thing, no two manufacturers' sensors are identical in the way they are measured, which means it's difficult to take an algae sensor from one manufacturer and compare it with a different manufacturer. That makes it critical to use the same instruments throughout, and as you can see in that photo, there's quite a few of those instruments deployed from the Lake Erie network. The measurement data is only as good as the calibration, so it's important to have a good calibration. And in order to get even better comparable data, we recommend calibrating the instruments together. The XO2 sonde makes that quite simple. You can actually connect 7 of the same sensor to the sonde for calibration in the same standard. And whoops, let me just go back here. And just to show you, this was on Monday, 24 XO2 sondes were calibrated in Toledo, and you can see the sensors there detached. Rather than calibrating each individual sonde, doing the conductivity, pH, algae, they just plugged in all those individual sensors into a sonde, did a quick calibration, and were able to distribute those sensors back to the other sondes. A little bit on the maintenance requirements. Obviously, you want to clean and check in known standards, recalibrate if necessary. We offer an annual tune-up service to check and make sure that the sensors are working within specification. And the annual cost for consumables, calibration supplies, maintenance items is generally about $1,500 a year for a fully outfitted sonde. Ballpark pricing for the sonde platform itself, given that the sensors are a la carte, so you can pick and choose what you want. The platform can range anywhere from $11,000 to $16,000. 11 assumes you have the total algae sensor and conductivity. Data buoy deployment would add about $10,000 to $20,000 depending on options. You have the data logger and interface. That can be anywhere from $3,000 to $5,000 depending on where you're transmitting, how you're posting that data, and where you're sharing that. Installation costs can vary from anywhere from $2,000 to $5,000 depending on the level of complexity. And then the calibration supplies generally less than $1,000, and the lab might already have access to pH buffers, conductivity standards, etc. And with that, we'll take some questions from the audience.
All right, thanks, Paul. One of our first questions here was for Brenda. Brenda, the question was the interpretation you had of the sondes is that it's more of a subjective, it's used as one of many things of what's happening. Is there how do you feel about making it more of an objective, the sonde, so at this level you do that?
Well, I think you pointed out in your slide when you were comparing the 2014 and the 2015 data, where you did this simple calculation of 1 RFU equaled about 1 microgram per liter, and 1 RFU equaled about 10 micrograms per liter. On a general basis, to write a book and say, this means this, no. But for an operator working at a plant where they're watching this data day to day, month to month, year to year, you develop a feel for what your own water is doing. And based on an individual year, like this past year, there wasn't a high level of toxin in the water, but there was a high biomass. You knew that going in, so as your biomass changed, you knew that your toxin was changing too. It just wasn't the same amount of change in toxin as had been in 14. But you could track that and trend that and use that to make treatment changes.
So if I understand, it's more about trend tracking than absolute values.
And familiarity with your own source water.
Sure. John, are there any other questions that we should be answering with the group here in our few minutes?
There were several questions earlier on about the particulars of sondes that I deferred to Paul. If those questions have been answered, great. If they haven't, maybe you could re-enter that question. And there was also a question right toward the end about DOM as a HAB proxy. Anybody want to pick that one up?
We haven't looked, so trying to look at if you have a sonde already, but it doesn't have the phycocyanin. You know, we haven't looked. You know, we showed that pH, you can use that in a presence-absence. If pH is rising, there might be a HAB. You know, that phycocyanin sensor really tries to isolate the bloom. You know, the problem with DOM is there's other things in the water that can contribute to it, and it might not be cyanobacteria. Same goes for turbidity. You know, if we look at turbidity during the bloom, the only thing that contributes to really turbidity during the bloom is the bloom. So the turbidity tracks the bloom. Now that changes in the fall once you get wind-driven resuspension, and now turbidity is driven by you know, inorganic matter in the water, and so you can't use turbidity anymore. So that phycocyanin and chlorophyll are, you know, isolating for green stuff in the water, and that's what we're concerned about. So again, there might be periods when you can use those other parameters, but you really have to be careful on how you interpret those. There's a few questions about this webinar. It is being recorded, and we apologize for some of the audio issues if you weren't able to hear it clearly. And we will make the recording available after. And if you guys have additional questions, you can either email the webinar organizer, or you can email Brenda, Paul, or myself. Look us up, find us, and we're going to make the slides available. And I'm also going to send links out to those EPA guidance documents that I had as well, so that I referenced. And any other materials that either Brenda or Paul wanted to include in that email, they can send that to me. I think we're out of time, and we'll try and answer any additional questions, follow up. We have your name. We have your email, and so we'll try and follow up if there's questions that were left unanswered. John, any closing remarks?
You're also encouraged to contact any of the speakers individually. You can find their email addresses, and we'll send them out as well. Each of these organizations, the University of Toledo, LimnoTech, and Fondriest, do a lot more than what you've seen here today. So you can speak to each of those speakers as a way of introducing you to other people at the organizations that may be able to help you with a broader suite of questions we've addressed today. And you can also follow up with the authors of those EPA documents if you have specific questions about toxin levels, newly emerging regulations, etc. So thank you for participating today, particularly people that are in different time zones. We know it isn't always convenient, but it's more convenient maybe than coming to Ann Arbor. So look forward to interacting with some of you again in the future.